Hey guys, so as you can see, it looks like people are tasting the rainbow here. And in fact, we figured out mathematically that the chances are almost zero that we cannot not taste the rainbow. We did find a couple people. So I think Catherine was not very good at tasting the rainbow. I was pretty bad. And Stephen was pretty bad. Where's Stephen's? 2 out of 7, yeah. Other than that, most folks seem to be able to taste the rainbow pretty good. So, what is this 4-step process and how can we get the next badge? Okay, so that's really important. And so this video, essentially, if you watch it, would be the one you would want to study for this next badge. So let's take a look. The name of this badge or procedure is called a one-sample z-test for P. Okay, so a one-sample z-test for P. Write that in. And so why is it a z-test? Well, notice that when we do our general formula, and then our specific formula, we're essentially calculating a z-score, just like we did back in Algebra 2, using this generic formula. And I'm not using p-hats because, again, we have to take the claim as true. So our general formula is, we're going to see this come up in some other chapters. It's our standardized test statistic. This is called the standardized test statistic. And we take our standardized test statistic and it's equal to whatever the statistics we gather. So that's our p-hat, minus our parameter. And so that's our accepted or claimed proportion. And we're going to put that over our standard deviation. Okay. So we need to then show our work here, right? So looking up in our problem, it looks like we had a random sample of 180 teenagers. Yeah, sometimes parents like to recount how difficult life was, such as having to walk 10 plus miles to school in the snow both ways. A random sample of, so that's our test statistic, right? We had 180 people we talked to. And 40% had heard stories from their parents or grandparents about this difficult suffering. So here it looks like you don't know how many said yes, but you could find out. What's 40% of 180? So what is 40% of 180? 72. All right, and again, we know that would reduce to 40%. Now, it says, does this data provide convincing evidence at this level that the proportion of all teenagers who've heard stories from their grandparents about how life was when they're kid differs from 50%? Okay, so we can't take our test statistic and make that our H sub O. Okay. We have to say they're asking us to test whether it differs, meaning it's just not 50%. That means we have to set this at 50%. So half the people hear it, half the people don't hear it. You took some data that it's less than that and a number that isn't 0.5. So essentially what this one is called is a two-tail or two-sided test statistic. So you're really looking for values that are either just show some sign of not being 0.5. So either very few people heard this or a lot more than 50% heard this, if that makes sense. Because this is not a greater than or less than sign, it's a not equal to. And we know our test statistic, right, our p-hat. This is our p, right? Our p-hat is 0.4. So that would mean this other side, that would be at least as extreme on the upside. Okay, so how did I figure that out? Well, 0.5 minus 0.4, 0.1. And 0.1 plus 0.5, that's 0.6. Okay. So let's play this out. I wrote this a little too high. Let me rewrite this. My hypotheses, H sub L, right? P is equal to 0.5. H sub A, P is something other than 0.50. All right, so what is our parameter? And we're copying this from the problem. The true proportion of all teenagers who have heard those stories. Okay. And our significant level, we're going to use pretty much our default. So we know the information we're going to type in our calculator, right? 0.4 minus 0.5, and we use the p hat, so 0.5 times 0.5 over 180, square root of the whole thing. Okay, but we can't really use normal distribution calculations unless we check our conditions. So those conditions are RIN. Is it random? Well, in the problem, it did say, yep, random sample of 180 teens. All right, is it independent? Well, I think we can say the 10% condition has been met. Because N is less than 10% of big N. So 180 is less than 10% of millions of teens. So this means sampling without replacement will still be fine. All right, and the last one, is it normal? Well, I think so. We asked a lot of people, didn't we? So that's N times P has to be greater than or equal to 10. So we talked to 180 people. Our proportion was 40. So those numbers look weird. Talked to 180 people, proportion's 40. So we said that's 72. That's greater than 10. And 180 times 0.6, which is the same thing as N times 1 minus P, right? That would be 118 or 108. 108. Yeah, and that's greater than or 10. So normal is going to be totally fine, and we're going to proceed. All right, so I do this calculation here, right? And I get a pretty low z-score. That's pretty low. So if I look, my test statistic, this is my test statistic, right? From 0.4. And then we're going to look at my p-value. And actually, I've got two areas under the curve. So if you want to go to your table A, let's see if I got my table A. My z-score is negative 2.68. Negative 2.68. 2.68. So it's this number 0.0037. 0.0037. 0.0037. And again, I have two of those. So that gives me, that's my p-value. Okay, that's pretty rare. So you actually do have evidence. So how do we write our conclusion here? We're going to say that assuming, which we have to, that H sub O is true, and that's that P is equal to 0.50, then what we're saying here is there's a 0.0074 probability of getting a p-hat of 0.40 or lower, or 0.60 or higher, purely by chance. That's essentially what we're saying, using probability. So that's essentially what it means, our p-value. So what conclusion can we come to now? We can now say that because we know that our p-value, 0.74, is less than 0.05, we do have sufficient evidence to or significant to support H sub A, that the true proportion of teens who've heard stories, it differs from, right? That's what our text says. How difficult life is when they were kids differs from 0.05. So definitely we have, it does seem like it would be something other than 0.1 or 0.5. Okay. Now, what does 2 say? Well, it essentially says a 95% confidence interval for the proportion of all teenagers who have heard stories from their parents or grandparents about how difficult life was when they were kids is this. Oh, yeah. So do you see 0.5 within the interval of plausible values? And it looks like we do not. So again, this is also evidence that we do have evidence that the true proportion of teens who've heard these stories differs from 0.05, because it wasn't even, that number was not even in the plausible values we created, and we're 95% confident that that captures the true proportion of teens who've heard that. So how do we say that in relation to our null hypothesis? We can say the null hypothesis value, I'm not going to say that in words though, so H sub O, which P is 0.50, is not contained in the confidence interval. So we have to make a decision, and our decision has to be we reject the null hypothesis. That's why we're going to reject that null hypothesis, because the interval gives other plausible values. Okay, so what are some key notes here? So that's kind of a complete answer that you'd need for your badge. There's kind of a lot going on there. We did kind of a one-sided p-test, and now this one's a two-sided. But we do kind of have to be prepared to do all three, and you will have a chance this Saturday to take your first badge if you want. Okay, so let's think of some important ideas here. Again, you saw us do a state, right? A plan, a do, and a conclude. So let's go through these steps. We want to list our parameter, all right? Our statistic, our hypothesis, and our alpha, right? In our plan, we want to name our procedure. We want to check those conditions. In our do, we want a general and a specific formula. We want to show our work. We want to show the test statistic. That's our z-score or z-value. And then the p-value, the probability we've created that outcome would happen merely by chance if, in fact, H sub O were correct. And in our conclusion, we want to actually interpret that p-value is what we did. We explained, like, well, what this p-value means. And then we want to include this decision, whether we fail to reject or fail to reject the null hypothesis. This includes this decision that we talked about and a conclusion of some sort, following a script, and don't forget your context. So you got to talk about, kids hearing stuff from parents. That's got to be in there. So the other thing that you maybe saw that was a little bit different in the one we just did here, right, is this was two-sided. So again, you're going to see time and again that our general formula was our standardized test statistic. And that's equal to the statistic minus our parameter all over our standard deviation. So this seemed pretty familiar, I hope, right? But this part was new. We did a two-sided test where instead of them saying, I think you're fibbing, I think it's something lower than that, or, I think it's higher than that, we had a alternate hypothesis where the p-value is just not the null value, something other than that. And so in that instance, we are going to have to multiply our p-value by 2. And that's why you saw me do that below. Okay, nice work, guys. We'll just give you a second to kind of soak that in. And I wish you good luck and a nice evening. Take care, guys.